Hey everyone, welcome back to the dining room shop. So this is the first part in a 2 or 3 part series on spindles, specifically their arrow motion and how to measure it. We're calling it the Precision Spindle Metrology series. I'm pretty excited for it and I hope you guys enjoy. So in the first part today we're talking about arrow motion mostly in the spatial domain and the basic concepts and vocabulary associated with that. Two fundamental types of arrow motion in the frequency domain, and then later on in different parts we'll get into the topics of sensitive direction, dive deeper into the frequency domain, data processing techniques, measurement techniques, and error separation. Should be pretty fun. So this video and the rest of these videos are not about anything I've discovered or developed. It's basically just a summary of information that is already out there, but I still felt it important to make, and here's why. So YouTube is, today, if you want it to be, a massively impactful educational platform. It's no exaggeration to say that my life and career thus far has been massively influenced and shaped by the things I've learned from YouTube. There are very good resources out there for spindle metrology, and we'll talk about them in a second. But none of that information exists in a concise, or we'll see how concise it really is, comprehensive video format. And I think it'd be nice if it did, so we're going to give that a shot. This is for engineers, machinists, practitioners of the mechanical arts, or really just anyone who has a curiosity in metrology, or is a enjoyer of small numbers, as I like to call myself. So I mentioned there are good resources out there. We'll start with those. You can consider this my bibliography. So first and foremost, the best resource on this topic is this book right here, Precision Spindle Metrology by Eric Marsh. This is the definitive text on the matter. Great figures, well written, easy to understand, and I would say truly comprehensive. Eric and his excellent students, Byron Knapp, Bob Greta, and Brian O'Connor, did great work on this thing. Unfortunately, in a distinct tragedy, it is no longer in print. So you can't buy it as of right now. Hopefully that changes. If you favor more dull bureaucratic writing, the ANSI standard B89.3.4-2010 is out there. It's called Axes of Rotation, Methods for Specifying and Testing. That exists and it defines some of the same concepts. I don't enjoy it quite as much. And the other thing is standards are not free. You have to pay for them just like books. So if you can get your hands on either of these, check them out, but you can now see why, after attending Byron's tutorial on the topic at the ASPE meeting this year, I was inspired to try and put out some free spindle metrology info on the internet. That's certainly enough intro for right now, so let's actually dive into it. Alright, so we have to start out with the most simple of definitions. What is a spindle? In the context of a machine tool or a measuring instrument, it's a machine axis with exactly one rotational degree of freedom, and ideally you would exactly constrain the other 5. In theory, that is. So what I've done here is I've 3D printed this little V-block fixture to form one of the most basic kinematic representations of a spindle. So we've got a shaft that sits in it like this, and we have 5 points of contact that comprise of 2 V's and one ball here on the back. Those constrain 5 degrees of freedom, and it leaves 1 remaining. So the front V here, when you put a shaft in that constrains it in the XY plane, which we're calling this plane here. So it cannot move in this direction or this direction. You add another V, another 2 points of contact, and now it's constrained in the theta X and theta Y direction. So it can't rotate like this, and it can't rotate like this. Finally, we add one more point contact in the back to constrain it in this direction Z, and now we're almost fully constrained, and the only remaining degree of freedom is this theta Z, which is our desired degree of freedom. So error motion is any motion in those degrees of freedom which we desired to constrain. But before I get any further into that, we first have to bring up runout. When talking about how good of a spindle is, you hear a lot of machinists and sometimes even engineers talk about runout. In reality, runout tells you nothing about a spindle's quality. Let me defer here to a brief clip from precision engineering titan Jim Bryan to clarify the issue.
This at all yet. Many people in the machine tool industry use the term spindle runout. Can you explain why this term does not describe spindle performance?
Sure. It is really true that throughout the world, the spindle runout term is deeply embedded. And to overcome that culture, the father to son, coming down from the Schlesinger book, is really very difficult. But the technical reason is that the runout of the shiny surface on the spindle has nothing to do with the function, nothing whatsoever. If you exaggerate the notion of grinding that surface in place, you will create a surface that's not round, that exactly compensates for the error motions within the axis of rotation. So the runout can be zero with a very bad spindle. Conversely, you can have that surface can be damaged, it can be eccentric, and this runout can be enormous with a perfect spindle. So if it is so that the runout can be bad for a perfect spindle, or the runout can be zero for a bad spindle, that's the proof that it has no meaning.
Or, put briefly, and this is not my quote, surfaces have runout, axes have error motion. I like that quote, but I really don't think I could explain it any better than that clip, though. I really love that explanation there. So, when you put your indicator on the surface of interest on a spindle, you may read zero, you may read a large number, but whatever that, when you're doing that, you're measuring runout, and that does not tell you anything necessarily about the spindle quality itself. So don't interpret what I'm saying right now as runout doesn't matter. Practically, the runout of your spindle taper is often very important. So, runout's a critical component of tool life and milling and micromilling applications. Runout determines how concentric your collet chuck can make two diameters on two opposite sides of a part on the lathe. So it is important from a machining perspective, but I want to draw a clear line between runout and the actual accuracy of the axis of rotation. Those are completely different topics. But anyways, back to error motion. So first, let's define what error motions can exist. We're not too worried about the causes of them right now, but you can play a fun game and imagine what influences and geometric errors might cause each type in your head as we go along. So basically there are three primary directions in which we can measure error motion that we care about. There's radial, which is error motion in the XY plane, axial, which is motion in Z, and tilt, which is the theta X and theta Y directions, which can be particularly annoying because it gets worse the farther away you are from the spindle. So depending on what you're using the spindle for, you may care about one of these directions but not the other. So for example, if you're turning an OD on the lathe like this, and you have a decent amount of axial error motion such that the spindle is pistoning in and out as you're turning your part, this is obviously very exaggerated. You'll probably never notice that, and you'll probably not care about it. Axial error motion is generally irrelevant in that case. But now if you're on a diamond turning lathe and you're turning a parabolic reflector and your tool is on the face of the part, suddenly that axial air motion is a serious problem. So that's starting to get into the topic of sensitive direction, which we're going to cover in detail in the next video, but it's worth mentioning now. So those are the three directions. Obviously, it's comprised of 5 degrees of freedom, but we group x and y together into the one category of radial, and theta x and theta y into the category of tilt. So those are the directions in which we can observe air motion. But let's back up and define the 2 fundamental types of air motion with respect to their periodicity. So what do I mean when I say with respect to their periodicity? All I mean is when those air motions occur with respect to the orientation of the spindle. So there are 2 types, synchronous and asynchronous. And you can have both of these in every one of the 3 directions we just talked about. So you have synchronous radial, synchronous axial, asynchronous axial, and so on. We'll look at synchronous first. And for discussion purposes, what we're going to do is imagine an almost ideal spindle that has only pure radial air motion. As this non-ideal spindle rotates, its axis also shifts and moves about in the xy plane, which is our air motion. In this case, I've approximated that by printing this shaft, which, unlike the one we showed before, is misshapen. That misshapenness, though, is uniform along the length of the shaft, so as we rotate this and it moves in our V block, it will shift and the axis of rotation will move around in the xy plane, but there will be no tilt because the air motion here is the same as the air motion here. So what we can do is I'll put this in this little elastic band here to help hold it down into the V, and we can put a marker in the front of it, and we can use this setup to trace out the path of the spindle as it rotates. So because this marker is at some radius and not at the exact center, we should expect to see a circle for an ideal spindle, but because we have radial air motion, we'll see something that is not quite a circle. So let's take a look at what we can draw out here. And yeah, that's not really a nice circle shape like we would expect to see. We get some shape to it. But the key point here is this air motion is exactly repeatable with every rotation. So you can see as I continue to rotate it, it's drawing the same shape every time. It's not that shape is not changing. So here it's a consequence of shaft geometry and errors in shaft geometry, but other influences such as forces from your spindle drive or other influences can also cause synchronous errors. But the fundamental point in the definition here is synchronous air motion is air motion that occurs at integer multiples of the spindle rotation. So you can have an air motion occur twice per revolution, 3 times per revolution, 20 times per revolution, it doesn't matter. But because it is an integer multiple, it occurs at the exact same spot during the rotation, every rotation. So what that means is, practically, Synchronous air motion is what defines the geometry of the part that your spindle produces. So in a lathe, it's, how round of a part you can turn. Or in a mill, jig bore, or jig grinder, how round of a hole you can bore with that spindle. Again, this is just talking in the radial case here. This concept applies in all of the directions, tilt and axial as well. In the lathe case, your radial plus your tilt synchronous affects roundness at a given location in Z and cylindricity of diameters and bores, while axial plus tilt synchronous affects the flatness of a faced part over a whole face, or the circular flatness at a given radius. So that's synchronous air motion, but what about asynchronous? So this time I'll start with the technical definition, and it's the opposite of synchronous. It's air motion that occurs at non-integer multiples of the spindle rotation. Some people like to say random air motion, which is one way to think about it, but it's not totally comprehensive, and I'll get into why I think that in a second. But first we can start with some more obvious sources of asynchronous air motion. So a good way to have your air motion occur at a non-integer multiple of the spindle's rotation is to have the cause of that air motion be completely unrelated to the spindle's geometry or position at all. So for example, if you're driving a spindle with a long belt and it's going fast and it's vibrating, the forces from that belt vibration will cause air motion in your spindle. And those forces are occurring at whatever frequency that belt is vibrating at. And that frequency might be completely unrelated to the frequency of rotation. So when you plot it, that error appears random with respect to spindle orientation. It doesn't occur in the exact same positions every rotation. Another example is, say, a poorly designed air bearing spindle. Let's say you've goofed your compensation, your orifices are too large or your graphite is too permeable, and now your spindle is exhibiting pneumatic hammer and it's vibrating and buzzing. That vibration is constant, and again, it's unrelated to rotation or the position of the spindle. Over time, it just appears, like a fuzzy noise floor superimposed over your actual synchronous air motion plot. Something like that, right? The thing is, asynchronous air motion is more than just vibration. Let's take a look at a type of spindle where asynchronous errors often dominate, and that is the ubiquitous ball bearing spindle. So that was a real ball bearing, but I've got this little gear bearing here, which we're going to use for demonstration. Let's assume this bearing is completely ideal, except for this one ball here. This ball, as I've drawn on it, we're going to say this ball is an oval. It's misshapen. So in this one direction, it's too large, and in the other direction here, it's too small. So it goes from almost not touching the races at all to being in interference with the races and shoving the spindle, causing a large force and causing the axis to shift like that, right? So every time the ball is in this orientation, you get a little blip of air motion. As I rotate this, we'll say this is 0 degrees here, right? It's lined up with the ball, and we have right now it's interfering, so we have air motion. Some little, if we're tracing it around here, you can imagine a blip and a shift in our axis of rotation. As we rotate this spindle around, boom, here we have another blip in our plot, and there's another one over there. Or one out's over here, right? And we've come around a full rotation, and the ball has, right now it's not interfering. It's caused a couple instances of air motion, but those are in, here, 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 and here, whatever. We can keep going around, and it's going to keep causing little blips of air motion. And eventually we come back to the point where it looks like everything should repeat. We're back three rotations later. But if we look, now the ball's in this orientation, or the oval ball is in this orientation instead of this. So we're no longer getting air motion at that position where we got it initially. And in fact, it follows that, every rotation, the air motion profile with respect to spindle orientation from this ball will be different. Eventually, it will repeat. So if I rotate this enough times, because it's the ratio of the diameter of the ball to the diameters of the races, right? So if I keep rotating this to the amount of times that it takes to where we've reached the least common multiple between those two circumferences, eventually that pattern will repeat. But depending on the size of the balls and whatnot, that may be a very large number of rotations later. I think a good analogy is also a spirograph, right? So if the ratio of the circumferences between the planet and the outer race is a nice clean multiple, we just get a nice pattern that repeats every single time, right? So here it's just an oval, and every rotation we get the same air motion profile. But if they're even a little bit different, then what we see is a pattern that looks like, and I'm blocking the camera here, let me move my hand, it looks like it's about to repeat, but it doesn't quite line up with the previous rotation. And then we have a new orientation, doesn't quite line up again, and then over many rotations of this ball, you sort of just get, eventually it will line up again, but eventually it just looks like a fuzzy cloud because it's processing with the spindle rotation. It's not a repeating pattern like that, or it's repeating, but it just takes many rotations to repeat. So you see why I don't like calling it random air motion. Parts of it can be considered random air motion, but asynchronous air motion from precession of balls like this, that's not really random, and in fact it's quite repeatable and predictable to the point where you can actually reverse it, and when you reverse the spindle, it will follow that same asynchronous air motion profile in the reverse direction, basically retrace its air motion steps, if you will. So I wouldn't call it quite random, but some parts can be random. But the point is, from one rotation to the next, you don't get the same air motion profile. And so over many rotations, you get an averaging, so it's just basically a fuzzy cloud superimposed over your synchronous air motion profile. And now intuitively you can start to think about what sorts of air motion would be most prevalent in different types of spindles. So like I said, in rolling element spindles, asynchronous often dominates. And that makes sense because you can imagine how there's a lot of stuff moving around and shaking at non-integer multiples of the spindle rotation. So your balls, the cage, the surface finish of those balls and the races and everything, none of that's going to happen once per revolution, 5 times per revolution, 7 times, that sort of thing. You get that more from the actual shape of your races, but a lot of the air motion comes from things that are processing and not happening at those integer multiples. So you get a lot of asynchronous. On the other hand, if you think about air-bearing spindles, besides the example I gave of a poorly designed air bearing that's oscillating, where can you get asynchronous from? And the answer is there's not a lot of opportunities for asynchronous to arise in an air bearing spindle because there's no contact between the surfaces. There's no rolling elements. And in fact, when you measure them, that's why you can even get sub-nanometer asynchronous error motions on hydrostatic and air-bearing spindles, just as a consequence of them having no contact between them. But what does asynchronous error motion affect? So if synchronous affects the shape of the part we produce, asynchronous affects the surface finish. So you can imagine how as your tool or cutter or whatever you're doing moves over the part, this random motion causes random variations in the surface texture that do not repeat with every revolution. Now in theory, due to the nature of these errors, if you just sat your tool on the part for an unlimited amount of time in the same position, eventually these errors would sort of average out and all the high spots would get knocked off. And you could approach a surface defined purely by the synchronous error motion. But practically, that's not really feasible just due to the nature of most cutting processes. You know, if you take your tool on a lathe and just let it sit there and not move for a minute, a lot of times it's going to start chattering and rubbing, and the finish is not really going to get any better. The closest you can come to doing something like this is grinding, where if you just keep sparking out, provided a perfectly stable machine that isn't growing away from the part due to thermal effects, you can pretty well average these errors away and sort of slowly knock off all the high spots until you have an extremely fine surface finish. I'll insert some photos here of a part that's been allowed to spark out continuously for something like 3 minutes on a cylindrical grinder. It was being side wheel ground, and this is just with a 60 grit, very open dressed wheel, so no really fine grit that's like polishing the surface or anything. This is just a result of letting it spark out for an extremely long amount of time and letting those high spots from the asynchronous error motion get sort of knocked off. It's completely impractical for any production environment, but it is a decent demonstration. And you could go for longer, but it's sort of a game of statistics for whether or not a high spot's going to get knocked off, and the less high spots there are, the less likely they are to be removed. So it's sort of asymptotically approaches a maximum. It doesn't just continuously improve at some linear rate. And when I say approaches a maximum, note that asynchronous error motion is a component of surface finish, but not the absolute determining factor of surface finish. So the maximum surface finish or the minimum surface finish you can achieve is, assuming zero asynchronous error motion, is still a function of your cutting process itself, like how you're physically removing the material from the part. Unless you're diamond turning, that cutting process is likely far more influential on the best surface finish you can achieve for a given setup. And even in diamond turning, your materials and speeds and feeds are obviously still important. It's not all asynchronous, but for the really high precision stuff, specifically diamond turning, that does start to become a factor in surface finish. Anyhow, those are the two types of error motion sort of in the frequency domain, the synchronous and the asynchronous. And I think we're going to call it there for part one. In the next video, we're going to talk about sensitive direction a little bit, how we actually measure these errors, process and look at that data, and even some fun error separation techniques for the really high precision stuff. So you may need to break that into 3 parts after hearing that out loud. We'll see how it all works out time-wise, but hope you guys enjoyed. Let me know if you have any questions down in the comments, and thanks for watching.